Bismillah ar-Rahman ar-Rahim. Welcome to lecture number 1 in optimization techniques. We will start with the definition of the optimization problem. We'll talk some terminology, some definitions, and things like that so that we will be familiar with the terms and terminology of the optimization problem. So our topic today is about the optimization problem. Okay. The process of optimization is the process of obtaining the best I'm looking for the best in the process. The word optimum is taken to mean either maximum or minimum. Okay. Usually optimum is stronger word than the best. يعني لما بقول optimum, the optimum value, it's better meaning than the best value. Okay, optimize is also, which means to achieve an optimum is a stronger word than the word improve. يعني أنا إذا بدي أتكلم عن optimum أفضل من استخدامي كلمة the best answer, the optimum answer. Optimum means either maximum or minimum. Using optimize as a verb to achieve the optimum is a stronger word than use to improve the solution. Okay. Optimization theory is the branch of mathematics encompassing the quantitative study of optima and methods for finding them. إذن the optimization theory هي فرع من الرياضيات المسؤول عن ال quantitative study of optima, find the optimum values, and the way that we can find them. Okay, optimization practice. Optimization practice is the collection of techniques methods, procedures, and algorithms that can be used to find the optimum. Okay. Several general approaches to optimization are available. As follows. There are several approaches for optimization, such as analytical approaches or analytical methods, graphical methods, experimental methods, and fourth, numerical methods. Those techniques will be explained later, but we will just mention those at the time being to let you be familiar with those methods at the time being. But we will come to explain them further in further chapters or in the coming chapters. Okay. The basic optimization problem. The optimization problem must be properly formulated. A performance criterion F capital must be derived in terms of n parameters. x1, x2, up to x sub n, as F, which is the performance criterion, is equal a function of those parameters, x1, x2, up to xn, where f is a scalar value or quantity. It can be the cost, can be the cost of a product in a manufacturing environment, or the difference between the desired performance and the actual performance of a system. What we mean here is that we started to formulate the optimization problem. So we have to find a function f, which is the performance criterion. Performance criterion is a function of certain parameters. Usually we call them x1 up to xn. F is the function of those parameters. Now, f is usually a scalar quantity. It's not a vector quantity. And sometimes it could be the cost of a product in a manufacturing environment. So you have so many parameters in the cost of the manufacturing. You produce something. You have so many parameters in the producing this something. Sometimes you know that you have to manage those parameters. Sometimes the raw material, you have to buy raw material. You have to buy some running cost. And you need to find the best way to get the product with the lowest cost, but with the very good quality. Okay. The other one is as is mentioned here, and could be the difference between the desired performance, the one that you are actually looking for, and the actual performance of the system. The difference between those two is the error. So you try to sometimes to minimize this error. So F here represents the error between what is really coming from a system and what is really desired from a system to behave. Okay. The most basic optimization problem is to adjust variables x1, x2 up to x sub n in such a way as to minimize quantity f. This problem can be stated mathematically as minimize f equals f of x1, x2 up to x sub n. F is usually referred as the objective or the cost function. So we either call it the objective function or we call it the cost function. So this is F. Okay. For shorthand notation, we will call X, and I'm putting a dash underneath so that to say that this is a vector. So I will let X as a vector equals to x1, x2 up to x sub n transpose, which means that this is actually equals to x1, x2 up to x sub n. Okay, so if we let X as a vector, instead of just putting all those together inside, we can say that this one can be written in a simpler way. Minimize f of the vector x for x belongs to E sub n. Okay, so we'll put it this way. And E here is the Euclidean space, the nth Euclidean, n-dimensional Euclidean space, where e to the power n represents the n-dimensional Euclidean space, the nth dimensional space. Okay. On many occasions, the optimization problem consists of finding the maximum of the objective function. So we need to maximize f of x which is equal to the minus of the minimum of minus f of x. So what is meant here is that the maximum of f can be achieved or obtained by finding the minimum of the negative of f, and then changing the sign of the minimum. So without loss of generality, we can always talk about the minimum. Whenever we need to find the maximum, we will multiply the objective function f by minus, minimize it, find the answer, and then multiply the answer by a minus sign, you get the maximum. Okay, this is the way how we will do it through this course. Okay. In many applications, a number of distinct functions of x need to be optimized. Simultaneously. Okay, so f of x is not only one function, it's a number of functions, f of x, f1 of x, f2 of x, and f sub m of x transpose. So the objective function is a number, or a vector of functions, f1 up to fm. Okay, so this is, we can write it in as this, f1 of x, f2 of x, f sub m of x. Okay, okay. For this type of functions, an objective function can be defined in terms of the L sub p norm as f is equal to L sub p. We'll put here three, this is as a definition, f is equal to LP, which is equal to the summation from I equals 1 up to m, the magnitude of f sub I of x to the power p, and everything after the summation is to the power 1 over p. So this is what we call the LP norm, the LP norm. Where p is an integer. Okay, for p equals 1, then f is actually equals to L1. So this is the L1 norm. which is equal to the summation of the absolute values of x's from I equals 1 to m. So the L1 norm is the sum of the absolutes, the sum of the absolute values. If P equals 2, then F is equal to L2, the L2 norm, which is the Euclidean norm, and this is equals to the summation for Fi of x magnitude squared from I equals 1 up to m, and this is to the power 1/2. To the power 1/2. And this is called the Euclidean norm. Okay? And this one will be minimized if the square root is omitted. If this square root is omitted, then what we have here is the minimization of the least squares errors. Minimization. So it's the minimum least squares errors if you take this one out from the L2 norm. Okay. Okay. In the case where P is equals to infinity, so if we take the L infinite norm, if we assume that there is a unique maximum of Fi of x designated f hat. So we call it f hat, such that f hat is equal to the maximum of Fi of x for I between 1 and m. So the maximum of the absolutes of f, we call it f hat. Then we can write f as L infinity, the infinite norm, to be equal in the limit, because we are approaching infinity, as P approaches infinity, to the summation of Fi of x magnitude to the power P from I equals 1 up to m, with a power of 1 over P outside. Okay, so this is the L infinite. As P goes to infinity, this is the definition of the L infinite. Now, I'm going to divide this by f hat and multiply it by f hat. So if we do this, then we have f hat limit as P goes to infinity, summation from I equals 1 up to m, magnitude of Fi of x divided by f hat, the whole thing to the power, to the power P, and the whole thing to the power 1 over P. Okay, so we introduce here f hat, we divide it by f hat because we know this one, we multiply it here, so it's still the same, this is equals to f and this is equals to L infinity. Now if we look at this, those values has a maximum for f hat, so the whole thing here in the terms and the summation will be to the power, there are values with less than unity, all of them to the power as p goes to infinity will be approaching 0, except one of them, which is when fi is equal to f hat, it's equal unity. And this one will give us this one will equals to 1. So this one will be equals to 1 multiplied by f hat, and we end up with f equals to f hat equals to the maximum for I between 1 and m, the magnitude of fi of x. Okay? Okay. So we can conclude here about L infinity that it is the minimization of the maximum. So L infinity norm is minimization of the maximum error. And the problem is said to be minimax problem. So when we talk about L infinity, we are talking about the minimax problem, which means that your function or objective function is the maximum error, and we will try to minimize f, which is the maximum error. So minimization of the maximum error is a minimax problem. Okay. We often have the individual elements or element function of f of x are modified by weights. W1, W2, up to W sub m. So we have f to be equal to the summation from I equals 1 up to m, W sub I, Fi of x magnitude squared. This is the weighted, we call it the weighted least squares objective function. Weighted least squares objective function. We multiply each fi by this w, so we call it a weight. All right, so just a remark here. The error in w sub I fi of x, if the error, the absolute error, almost equal epsilon, then the error in fx by itself, fi of x by itself, is almost equals to epsilon over the absolute value of w sub I. So what does that mean? It means that if you need to get a lower error in certain f, multiply it by a large weight so that you can get a small error at the end. So you can notice here that the actual error of fi is epsilon over the weight. So as long as you choose the weight to be very large, the error in this particular fi will be very small. Okay, so let me write this down. So if a large positive weight Wi is used with fi of x, this means that a small residual error is achieved in fi of x, okay, as seen here in this equation. Okay. All right. So let me move to the general structure of the optimization algorithm. I'm going to write it here down. The general structure of optimization algorithms. So the general structure of optimization algorithms includes 4 steps. The first step is the initialization. So step 1, the first step 1, actually, the first item will be to set k equals 0. So we have a counter. The counter is k. K will be our number of iterations. So our first iteration will be k equals 0. And so we initialize the counter by 0, and we initialize x0. So you have initial values to set k equals 0 and initialize x to be equal to 0. Now, based on this, we take x0 and we compute f0, which is equal to f of x0. Okay, so this is the first step. Initialize the values, compute the initial cost function based on the initial values. Okay, then step number 2. The first element in step number 2 is to set k equals to k plus 1. So we now start doing the steps. Step number 2 is put k. So increment the counter, b, compute the changes in x of k given by column vector delta x sub k, where this delta x can be, actually it's a vector of data. So delta x sub k is equal to a vector of delta x1, delta x2 up to delta x sub n. Okay, so this is the vector by using an appropriate procedure. And actually here comes the way that you are doing or modifying those delta. It depends on the technique that you are using. And this is, but we are talking here about the general structure, so I'm not gonna use specific values or specific procedure to do delta x. We'll come to this later. Okay, C, set xk equals to x of k minus 1 plus delta of xk. D, compute fk equals to f of xk. And delta fk equals to fk minus 1 minus f of k. Okay, so this is how the procedure. Step number 2, increment the counter, compute delta x's, change x by this formula, find the new optimization function or the performance function or the objective function fk, and find the delta fk. Okay. Step number 3, check if convergence has been achieved by using an appropriate criterion. For example, by checking delta fk and or delta xk. If this is the case, so if you have convergence, continue to step 3, continue to step 4. This is the case, continue to step 4. Otherwise, go back to step 2. So in step 3, we go and check for convergence by checking delta fk or delta xk. If this is the case, that means if we have convergence, then we have to continue to step 4. If we don't have convergence, then we have to go back to step number 2, where we increment the counter and do the other steps here. Okay, step number 4 means that you find, or you are in convergence, you find the convergence. So step 4, A, output x star equals xk, and f star equals f of x star, and B, stop. So you end the end of the procedure. Okay, the column vector x star, which is equal to x1 star, x2 star, up to x sub n star, which is equal to xk, is said to be the optimum solution, or simply the minimizer. F star, sorry, is said to be the optimum or the minimum value of the objective function. Okay, just for a note here, when we say about convergence, we say that, okay, if my delta, the absolute value of delta fk is equal to the absolute value of fk minus, or fk minus 1, fk minus f of k minus 1, f of k minus 1 minus fk less than epsilon sub f, and we'll take about delta xi less than epsilon x for I equals 1 to up to m. So the convergence means that if f of k minus 1 minus fk is less than epsilon f, where epsilon f supposedly to be set in the initialization, and delta xi is less than certain epsilon for all values of delta xi's from I equals 1 to m, or one of those or both of them, one of them or both of them should be taken into consideration when we are discussing convergence. Okay, thank you very much. We'll stop here and we'll continue our lecture next time. Thank you.